This is lesson 3.2 or unit 3, lesson 2, adding, subtracting, and multiplying polynomials. So my lesson essential question is, how do you add, subtract, and multiply polynomials? And at the end of this lesson, we'll be able to add, subtract, and multiply polynomials. So first thing I want to do is I want to look at an example of adding polynomials. All right, example 1, add and subtract polynomials. So how do you add the polynomials? So to add polynomials, I use the commutative and associative properties to group like terms. Then I combine those terms together. So for example, 6x cubed plus 4x plus x squared minus 7 plus 2x cubed minus 8x squared plus 3. So I have a polynomial and a trinomial, 3 terms, try. Okay. I'm going to look for terms that are the same. So they have the same variable raised to the same power. That's what I mean by like terms, okay? So 6x cubed and 2x cubed, which are both in red, both have an x cubed. So I can add them together, okay? The 4x is just kind of hanging out by itself. There's no other x values. X squared, the green, and negative x squared, both are x squared. And then, of course, negative 7 plus 3. Really recommend, if possible, to get multiple colored pens, highlighters, whatever works best for you. And actually, when you start going through this, practice highlighting them so you can easily see where the like terms are, okay? So I have 6x cubed plus 2x cubed, which is 8x cubed. 4x just tags along. 8x squared minus 8x squared is negative 7x squared. And then negative 7 plus 3 is, of course, negative 4. Okay. I then write this in standard form, which, remember, is from largest exponential value to the smallest. So 8x cubed minus 7x squared plus 4x minus 4. Okay. Subtracting is very similar to adding, except with this minus sign, we're actually going to have to distribute that minus sign to everything that's inside that second set of parentheses. Okay. So just like we did way back in like 7th, 8th grade math, even some pre-algebra, some algebra 1, you're distributing this negative value, just like we did with integers, just like we did with rational numbers, all of that, okay? So to subtract polynomials, I use the commutative and associative properties to group like terms, then combine like terms. So again, I need to change this minus basically to a plus. In order to do that, I have to distribute it to each one of these. So now I have negative 2x squared y squared minus 3xy squared plus 2x squared, okay? Now I can combine like factors together, the 3x squared y squared minus the 2x squared y squared plus 2xy squared minus 3xy squared plus 6x squared plus 2x squared. Okay, so when I do that, I get x squared y squared minus xy squared plus 8x squared. So the degree of a multivariable polynomial is the greatest sum of powers in any term. So for example, 2 and 2 would give me 4, so that's actually the greatest sum of powers. Okay, so that's why this is first and not xy squared, okay, or 8x squared. Okay. Xy is next because x to the first power, so 1 plus 2 gives me 3, and then of course the 8x squared. All right, so let's try it out. Add or subtract the polynomials. So I have 4a to the 4th minus 6a cubed minus 3a squared plus a plus 1 plus the quantity a, 5a cubed plus 7a squared plus 2a minus 2. So the first thing I want to do is I want to look at my like terms. So I have 4a to the 4th, and I have nothing else with that. So it's just going to hang out. Okay. Then I have negative 6a cubed plus 5a cubed. And then I have negative 3a squared plus 7a squared. Then I have a plus 2a, and then I have 1 minus 2. So the 4a to the 4th just gets to hang out by itself. Negative 6a cubed plus 5a cubed is negative a cubed. Negative 3a squared plus 7a squared is plus 4a squared. And then a plus 2a is 3a, and then 1 minus 2 is negative 1. Okay, subtraction. I'm going to copy this first polynomial. Then I'm going to distribute this minus sign to everything that's inside the second polynomial. So positive 3a squared b squared becomes negative 3a squared b squared. Negative becomes positive, and positive becomes a negative, whereas fractions on. Now I can combine my like terms. So I have 2a squared b squared, and then I have a minus 3a squared b squared. I have 3ab squared. I don't have any other. I have this one right here, minus 7ab squared. And I have negative 5a squared b. And then plus 9a squared b. Okay, I want to double check that I have everything. 2a squared b squared, yep. 3ab squared, yep. Negative 5a squared b, yep. Negative 3a squared b squared, yep. 9a squared b, yes. And negative 7ab squared. Okay, have everything. So now I can combine my like terms. So I get negative 1a squared b squared. 3 minus 7 is negative 4, so negative 4ab squared. And then a squared, negative 5 plus 9 is positive 4a squared b. Okay. You can leave it in this order. Technically, it is correct. Okay, so negative a squared b squared does come first because 2 plus 2 is 4. I like to, if I have 2 with variables and exponents that are equal, so like a to the first b squared is 3, a squared b to the first is also 3. I like putting the variable that comes the earliest in the alphabet first. So in this case, it would be 4a squared b minus 4ab squared. Really, either is correct, but I'm going to put it in that order because of the fact that it's a squared b, so there's still 3 here, and 1 plus 2 still gives me 3, but there's more a's, and a comes first in the alphabet. All right, example number 2, multiplying polynomials. How do you multiply the polynomials? Okay, so I have 2m plus 5 times the quantity 3m squared minus 4m plus 2. So just like we've used the distributive property in the past, we're going to use the distributive property again. Okay, so I'm going to multiply 2m times this polynomial, and I'm going to multiply 5 times this polynomial. Then I'm going to add everything together, get all my like terms together. So 2m times 3m squared is 6m cubed minus 8m squared plus 4m. 5 times the polynomial is 15m squared minus 20m plus 10. Okay, then I'm going to combine my like terms. 6m cubed gets to hang out by itself. Negative 8m squared plus 15m squared plus 4m minus 20m plus 10. And 10 also gets to hang out by itself. Okay, when I combine that, I get 6m cubed plus 7m squared minus 16m plus 10. And that's it. Okay. So again, multiplying polynomials. This one is 3 binomials together. Okay, so I multiplied the 2 binomials first. Doesn't matter which 2 because it's multiplicative. So you're gonna get the same answer in the end. Okay, so usually just go with the first 2, makes your life easier. So mn plus 1 times mn minus 2 gives me n squared minus 2mn plus mn minus 2 times mn plus 4. Okay, combine this, make this simpler for yourself. So I get n squared minus mn minus 2 times mn plus 4. Repeat the process. Okay. When I do that, I get m cubed n cubed plus 4m squared n squared minus 4 minus m squared n squared minus 4mn minus 2mn minus 8. Okay, then I combine my like terms and I get m cubed n cubed plus 3m squared n squared minus 6mn minus 8. All right, now we get to do it. All right, so multiply the polynomials. 6n squared minus 7 times n squared plus n plus 3. So I'm going to multiply 6n squared times n squared plus n plus 3. And then I'm going to add negative 7 times n squared plus n plus 3. It's really important that you include these signs, okay? Otherwise, you will get an incorrect answer. So I get 6n to the 4th plus 6n cubed plus 6 times 3 is 18n squared. Okay, plus negative 7 times n squared is minus 7n squared minus 7n minus 21. Okay, I'm going to add my like terms together. So I have 6n to the 4th plus 6n cubed. 18n squared minus 7n squared is 11. Plus 11n squared. And then minus 7n minus 21. 6n to the 4th plus 6n cubed plus 11n squared minus 7n minus 21. Okay. So now I have mn plus 1 times n squared n minus 1 times mn squared plus 2. Okay, so I'm going to start with my first two first. I'm going to ignore the third polynomial right now. Binomial. Oops. I'm just going to focus on these two. Really like saying mn times m squared n minus 1 plus 1 times m squared n minus 1. Okay. When I do that, I get m cubed n squared minus mn plus m squared n minus 1. Okay, so the mn times m squared n gives me the m cubed n squared. mn, it's like saying m&m. mn minus 1, or times negative 1, gives me negative mn. And then 1 times m squared n gives me m squared n. And then 1 times negative 1 gives me negative 1. And looking at this, there's nothing that I can combine. So I'm just going to multiply this times my third binomial. So when I do this, I get m cubed n squared times mn squared plus 2 plus mn times mn squared plus 2 plus m squared n times mn squared plus 2 plus a negative 1 times mn squared plus 2. Okay. So looks really complicated. I'm writing out each time. Okay. So m cubed n squared times mn squared gives me m to the 4th n to the 4th plus 2m cubed n squared. Okay. Negative mn times mn squared gives me negative m squared n cubed minus 2mn plus m cubed n cubed plus 2m squared n minus mn squared minus 2. Now I get to combine my like terms. So m to the 4th, n to the 4th, that's by itself. Okay. 2m cubed n squared. I have any other 2m cubed n squared? Does not look like it. So plus 2m cubed n squared. 2 and 3, nope. 1 and 1, no. 3, 3, no. 2, 1, no. Okay, so I don't have any like terms to combine, so I want to put them in the correct order. 4, 4 is 8. 3, 2 is 5, but 3, 3 is 6. So I have plus m cubed n cubed. Then I have 3, 2, and 2, 3. They're both 5s, but I have more m's in this one. Okay. This is 2, but this is 3, and this is 3, so plus 2m squared n minus mn squared. And then I have minus 2mn minus 2. That is my final answer. Or easy as that looks. All right, example 3 is the set of polynomials closed under addition and subtraction. Explain. The set of real numbers is closed under addition if a and b are real and a plus b equals c, then c is also real. Add two polynomials. So if I'm adding these two, okay, I can see that a sub n x to the nth plus b sub n x to the nth equals a sub n plus b sub n x to the nth. Okay. So adding like terms doesn't change the variable factor or factors of the terms, only the coefficient. Okay. It continues in the same manner. Since a and b are real, a plus b is also real. The exponents are unchanged. The sum is still a polynomial. So the set of polynomials is closed under addition. Using the same logic, you can determine that the set of polynomials is closed under subtraction. Is the set of monomials closed under multiplication? Please explain. So yes, they are. The product of two or more monomials will always be a monomial. Coefficient will be real because the real numbers are closed under multiplication. The variable terms in the product will still have whole number exponents because the whole numbers closed under addition. All right, so example number 4, write a polynomial function. Carolina makes wind chimes to sell at the local street market. As Carolina produces a greater number of wind chimes, she can lower the price per unit. The function v of x equals 48 minus 2x relates the price v to the number produced x. The cost c of making x wind chimes can be represented with the function c of x equals 12x plus 64. How many wind chimes should Carolina sell each week to maximize her profit p? So I can write a function for revenue r by multiplying the price v of x equals 48 minus 2x of each item by the number sold x. Okay, then I write the function for profit p. So p of x equals r of x minus c of x. So the profit equals the revenue minus the cost. So 48 minus 2x times x minus 12x plus 64. So I can, of course, simplify this function by multiplying x through. I get 48x minus 2x squared minus 12x minus 64, which simplifies to negative 2x squared plus 36x minus 64. So Carolina's profit function is p of x equals negative 2x squared plus 36x minus 64. So Carolina's profit is modeled by a quadratic function. The domain of the function is the set of whole numbers. Her maximum profit corresponds to the vertex of the graph. Carolina's best business plan is to produce and sell 9 wind chimes per week for a weekly profit of $98. All right, so let's try it out. The function v of x equals 48 minus 2x relates the price v of Carolina's wind chimes to the number produced x. The cost of Carolina's materials changes so that her new cost function is c of x equals 4x plus 42. Find the new profit function, then find the quantity that maximizes profit and calculate the profit. Okay. So we know that Px equals, so your profit equals the revenue, R of X minus your cost. So I know that my profit so I know that R of X equals 48 minus 2x times x. Okay. So remember that the revenue is multiplying the price of each item by the numbers sold. So this is the price times the x numbers sold. Okay, so I substitute that in. So I have 48 minus 2x times x minus the cost, which is 4x plus 42. Okay. So when I simplify this, I get 48x minus 2x squared minus 4x minus 42. Combining like terms, I get negative 2x squared plus 44x minus 42. Okay. So that is that when I graph it, my graphing calculator. Okay, so I have negative 2x squared plus 44x minus 42. Let me zoom out a little bit and up. Okay, so here's my vertex, which is 11, 200. So if I make 11, if she makes 11 wind chimes, she will make a maximum profit of $200. So the quantity that maximizes the profit is 11 wind chimes, and the profit is 200. Gosh. All right, example number 5, compare two polynomial functions. Carolina's profit function y equals px is represented by the graph. Her neighbor Kio's profit from selling X decorated flower pots can be modeled by the function shown. So here's Kio's flower pots and Carolina's wind chimes. Find the y-intercept of each function. Who would lose more money if neither person sold any items? So the y-intercept of P of X, so Carolina's, is negative 64. Negative 64. If Carolina does not sell any wind chimes this week, she will lose $64. Carolina has startup costs, which she pays whether she sells any items or not. I can substitute 0 for X in R to find the y-intercept. Okay, so I substitute it in here. If I substitute that in, I get 0. The y-intercept, if R is 0, if Kio does not sell any flower pots, he does not lose any money. So Kio has no startup costs. So I can also interpret the end behaviors of the functions. So the domain for each function includes only non-negative values. So what is the end behavior as x approaches infinity? The graph of P of X shows that the end behavior as x approaches infinity is y approaches negative infinity. So as I'm approaching, so x gets bigger, y is getting smaller. I can rewrite the function r in standard form to identify end behavior. So x times x minus 3 times 10 minus x gives me negative x cubed plus 13x squared minus 30. Okay. Because the leading coefficient is negative, we know that as x approaches infinity, y also approaches negative infinity. So Keo and Carolina each have a finite number of items they should sell to maximize their profits. So compare the profit functions of two additional market sellers modeled by the graph of F and the equation x plus 1 times F, or 5 minus x. Compare and interpret the y-intercepts of these functions and their end behaviors. So looking at this, the x so the y-intercept is 0 for F. The y-intercept is 0. Okay. So, and the y-intercept for G, so if I plug in 0, 0 plus 1 times 5 minus 0 equals 1 times 5, which equals 5. So the y-intercept for G is 5. So the seller using G earns $5 while producing no products, but the seller using F is 0, earns $0. So the seller for the graph of F, if he produces no product, he makes no money. Which is probably good. Okay. Not great, but not horrible. If you don't produce anything, you don't lose anything. The end behavior of F is as x approaches infinity, y also approaches infinity. Okay. And then as x approaches negative infinity, y also approaches negative infinity. For G, the end behavior, okay, so multiply x plus 1 times 5 minus x equals 5x minus x plus 5, okay, 5x minus x squared plus 5 minus x, which equals negative x squared plus 4x. So looking at this, I have a negative leading coefficient and even term. So the end behavior is going to be as x approaches infinity, y approaches negative infinity, and as x approaches negative infinity, y will approach negative infinity. So this means that for the seller using F, after 5 products, the more products he makes, the more money he makes. The seller using G only makes money for 0 to 5. All right, so concept summary, adding and subtracting and multiplying polynomials. To add polynomials, use the associative and community properties. To group like terms, then use the distributive property to combine like terms. Okay, so to subtract polynomials, distribute the factor of -1, then group and combine like terms. To multiply, use the distributive property, then group and combine like terms. All right, and that is the end of Unit 3, Lesson 2.